Hi everyone, welcome to the video lecture for ME 296. The topics today are Kirchhoff's law, the two methods of circuit construction, and the two methods of reducing a complex circuit into simple equivalent circuits. So first is a brief review of Kirchhoff's laws. Kirchhoff's laws are restatements of the laws of conservation of energy and conservation of mass. And these can be derived from the Maxwell equations, but we're going to leave that for supplemental material and instead focus on the more fundamental logic behind them. So the foundation behind Kirchhoff's laws is that circuits are effectively closed systems. If we lose energy in our circuit, it's being replaced by the voltage source. And because of this, the energy in our circuit is effectively conserved. This means the heat energy lost from a resistor is replaced by our battery or the wall outlet. And so we keep the energy the same. And if we do lose a few electrons from our circuit, they're going to be replaced by the current source. And because of this replacement, the number of particles, and therefore the mass of our system, is going to remain constant as well. Because two things are being kept constant, there are two forms of Kirchhoff's law. And the first is the law of conservation of voltage. It states that the voltage applied to a circuit by a source is equal and opposite to the voltage lost across the components of that circuit. And the second form of the law is conservation of current. It states that the current provided by a source is equal to the sums of the currents through each path. And both of these, what they really mean is that what you put into a circuit, you get out. All right, so that was a brief review of Kirchhoff's laws. Now on to circuit construction methods. There are two methods of circuit construction. The first and simplest is series construction. By definition, if components are sharing the same current, they are in series with each other. In practice, building a series circuit means that the output of one device connects to the input of the next. And I want everyone to please note that sharing current does not mean equal current. It is the same electrons in different devices at different times and not two equally valued currents. And as an example of how devices might behave when placed in series, let's look at several resistors in series and how they would combine their behaviors. We know that due to Kirchhoff's law, the voltage provided by the voltage source is equal to all the voltage lost across the entire circuit, which in this case consists of resistors. So we can write that as V total is equal to the sum of the voltages across the resistors. And now we can use Ohm's law to help us out, because V total equal to the sum of the individual voltages isn't entirely helpful to us when we're trying to get the value of the resistance in our circuit. So we use Ohm's law to replace the voltage with the current times the resistance. So we get the form I total times R total is equal to the sum of the individual currents and resistors. But we also know that because they're in series, by definition, I total is equal to all of the currents and the resistors. In fact, it's the same current and not just equal, it's the same one. So we can drag those out, factor it out, and drop them from our equation. And now all that's left is the statement of resistors, where it says that the total resistance in our circuit, R total, is equal to the sum of the individual resistances in series. Now on to parallel construction. Components are in parallel when they have equal voltage and are on different paths in the circuit. We can take this to mean that if several components are fed from the same point and eventually come back together, they are in series. So how do resistors in parallel behave? The resistors have different currents due to being on different rails, and this is an indication that Kirchhoff's current law might be helpful. The total current in a parallel circuit is equal to the sum of all the currents in all of the available paths. So from the example circuit shown on the screen, the total current in the system is equal to the current of all three resistors. Okay, that's law of conservation of current. So first we write that down. We're trying to find the resistance value. So once again, we use Ohm's law to substitute in an equivalent equation that does include resistance. In this case, it's voltage total over resistance total is equal to the sums of the individual voltages over the individual resistances. And we know that by definition, In a parallel circuit, the voltages are all equal. So we can once again factor out the voltage and drop it from our equation. And then what we're left with is the inverse of the total resistance is equal to the sum of the inverse resistances of all the individual resistors. Please note that it says that the inverse of total resistance is equal to the sum of the inverses of total resistors, individual resistors. Don't forget all the inversions. There are two. So to sum up these methods of construction, series construction means that current is the same across all components in series with each other, and parallel construction means that voltage is the same across all components in parallel with each other. Now these two methods can be combined into the same circuit, making analysis a little harder, not too bad. What we do is we start with what we know is easy to combine and work our way out from there. So the initial circuit at the top, we see that R1 and R2 are in series with each other, and all the other components have some complex relationship. R3 and R4 are not in series with each other because R3 does not share the same current as R4 because current is split from the top and bottom path. And the same with R1 and R4. And R1 and R3 are not just in parallel with each other because we have to take into account the effect of R2 on that top path. So what we know the most about here is R1 and R2, and they're just in series with each other. So we start there. We combine them into an equivalent resistor, and now we have a more simple circuit. We know that R12 is in parallel with R3. So we combine that into R123, and now we have our reduced circuit after we combine the R4 in series with R123. So because of this, these methods of integrating parallel and series construction resistors, we can take arbitrarily complex circuits and reduce them to equivalent circuits. So equivalent circuits. Why can we do this mathematically? Well, we can do it because circuits are linear systems, and linear systems satisfy two conditions. And the first is that if you add two inputs to the system, it is the same as adding the results together from individual inputs. For example, let's take Ohm's law. If we have two currents we're running through a resistor, is the output voltage going to be the same as if we did both currents individually and added together the voltages at the end, or just add together the two currents and then run it through Ohm's law? So if I1 is equal to 2 amps and I2 is equal to 1 amp, is our voltage going to be the same for both methods of adding them together? Looking at the example, yes it is. 2 amp plus 1 amp is 3 amps times resistance. So resistance is going to be 3 amps times R. And if we do it individually, we get 2 amps times R plus 1 amp times R. Factor out the R, and once again, we get 3 amps times R. So it's equivalent. That's the condition 1. Condition 2 is that a constant coefficient multiplying the input must simply multiply the output. So let's check again. If we have current 1 being 2 amps and we have a constant coefficient of 2, if we multiply the amperage inside of Ohm's law by 2, do we get out twice as much voltage as if we took voltage and multiply it by 2 at the end? Checks out. So it satisfies both conditions for linearity. So because of these properties, we can take arbitrarily complex circuits and then reduce them to simple ones. And just like Kirchhoff's laws, there are two equivalent circuits that people like to use. Each one is based off of one of Kirchhoff's laws. And the first is the Thevenin equivalent circuit. A Thevenin equivalent circuit is a single voltage source and a single resistor in series with each other, and usually attached in series with a load. More on what constitutes a load in a moment. So this is the most common one that people learn first. And the second one is the Norton equivalent circuit, which consists of a current source, not a voltage source, and it's attached to a resistor in parallel. So what is a load? A load is a part of the circuit that we did not already analyze. Think of a battery. Inside of the battery is pretty complicated, but someone has already gone through and done all the work to simplify it to a voltage source or a current source with some output resistance across the two terminals of the battery. And when you plug that into something like a remote control, we don't have to reanalyze the components of the battery in order to get their effect on the rest of the circuit, because we've reduced that complex internal working of the battery into something simple. And I think it's best to understand this concept through example. So let's do one. So let's do the Thevenin example. The first step to getting a Thevenin circuit is to treat each voltage source as a short, or just a wire with no components, and each current source as a break or a gap in the wire, so no current can flow through it. And now we're going to solve for the equivalent resistance from the point of view of the load. In our case, this is going to be L plus and L minus. We determine that the total resistance the load will see is 3.5 ohms. So to determine the voltage that the load will see, we put everything back, and then we solve for the current loops, where the load does not constitute a component of a loop. So to determine a current loop, you can trace your finger from each source through the circuit and then back to the source. And then each complete path that your finger makes back to the source is one current loop. And in this example, we can see that there are 2 loops, and both of them interact with R3. So it is possible for multiple loops to interact with the same component. And because it's a linear system, we know that the total effect across resistor 3 is just going to be the sum of the individual loops I1 and I2. So we know that I2 is 2 amps because we have a 2 amp source there. So we just need to solve for current loop 1. So we're going to use substitution in our system of equations, and we'll solve it and see that I1 is 0.583 amps. And then the final step is to determine the voltage that the load will see. Based on the construction of the circuit, the load is in parallel with resistor 3, and therefore resistor 3 and the load must have the same voltage across. So using the current across resistor 3 and the resistor value, we find that the voltage is 5.167 volts. And now we know that if we plug something into L plus and L minus leads, it will see 3.5 ohms in series and a pinch more than 5 volts. To determine the Norton equivalent of the same circuit, we can just take advantage of Ohm's law and solve. So the current is equal to voltage over resistance, and we already know the voltage and the resistance, so we can just use that to find our current and get 1.47 amps, which is in series with the resistor. And these values are interchangeable due to the Ohm's law relationship. It's the same resistance value for both. The voltage and the current are just part of the same Ohm's law triangle. So each of these types of equivalencies have their own use. If we need to know the current that will flow into the load, we would use the Norton equivalent circuit. The load resistance and the Norton resistance will share the supplied current proportional to the resistance values. For example, if the load resistance is half the Norton resistance, the load will receive 2/3 of the supplied current based on sharing. Similarly, the Thevenin circuit can show how much voltage the load will receive. Because voltage drop is proportional to resistance, if the Thevenin resistance is much higher than load resistance, very little voltage will drop across the load. All right, that's all for right now. More in the next video lecture. Thank you for listening.